theory. Our presenter is Mr. Dr. Poki Wong, and this presentation is of a paper that was written by his son, when he was a junior at UMass.
Thank you. This is the last one. I will move it as quick as possible. Everybody tired, want to go home. I understand that. And so that's the title. This was done by Adam Wong when he was a junior under Professor Herders, who taught the number theory at UMass. Now, first I show you the references he had so far. He tried very hard to get Martin Gardner's paper, and as a result, he had to write to the Scientific American and get the associate editor indicate where was this old paper located, and then he get the old paper, and from there get a lot of information for what happened in the old version. Of course, he's taking the class from Professor Herders of the UMass Boston, where he learned the number theory. And so this the only two references he has. Now the acknowledgement simply just for two people that he should acknowledge to. One is Professor Herder. He's a teacher, and the other is the lady, I think, is Miss Primus of Scientific America. Now the problem, let me state a little bit to simplify it. The problem is like this. It was a long time ago. I don't have the paper here. A long time ago, Professor Herder just changed the problem a little bit. Let me describe what it is there. W1, W2, W3, W4 is 4 different persons, even though when he used it as a woman. The older version by Williams, it was a sailor, but it doesn't matter. There's no offense to anyone at all. It has to be some people. Now the game is like this. You had 4 number of person, 4 different person. They are collecting coconuts and assisted by a monkey. And every time the pile of coconut, the number is unknown. They collect the coconut and divide it into 4 pies. Suppose there's four person there. And always have one left and give that one to the monkey. Okay? Now, here the problem become very troublesome. Suppose I had more than 4 person there playing the game. Suppose I had, say, 2,000 people playing the game. This become a big problem because you use the congruence, number theory of linear congruence. You end up, you have to reduce many simultaneous equations reduced into the Diophantine equation of 2 unknown. But that reduction is very difficult. So on that basis, he have been seeking, because he asked me my opinion, maybe we can solve it in another way. Because he was supposed to write a computer program to solve the problem.
Sorry, can you repeat the problem in the sense that you have a...
Yeah, you have pie of nut. I don't know how many is there. Right. You have a finite number of people dividing the nuts together. But always the whole pie of nut divided by that number of people, you have always one left and give it to the monkey. That's the problem.
So what's the problem?
The problem is how to find out how many, it's not finished yet. So one of the persons, say W1, after he divided into 4 pies, suppose it's 4, he hide 1 pie of the nut. And the other 3 people doesn't know, means he is cutting the deal, so to speak. He's trying to hide something, hide his share. And then the next person also do the same thing. Now let me read it to you, maybe from the article. Now that's not my word, let me quote. Maybe that would be more understood by Professor Herder's, I think that's a safe way to say so. A pie of cocoa nuts was collected by 4 women, assisted by a monkey. During the night, one of the women arose while the others were asleep and divided the nuts into 4 equal shares, with 1 nut left over which she gave to the monkey. She hid 1 share and put the rest of the nuts into a single pie and went back to sleep. In turn, each of the other 3 women went through the same procedure, and in each case there was always 1 nut left to give that to the monkey. In the morning, the 4 women divide the remaining nuts into 4 equal shares, and again have 1 nut left over for the monkey. The question: what is the smallest number of nuts which could have been in the original pie? That is the question. And he won, I think Professor Herder won all his number theory students to write a program to solve this problem. So Adam, I think, of course, got his assignment. He did ask me a little bit problem, how to solve it. But mostly, this assignment is really half done by him, half done by me. I give him only the idea. And he knows he should be able to figure out how to apply this and obtain the result. And now, let me go on again. Is there any question on the problem right now? Any question on the assignment, on the problem from the audience? Yes.
Was it supposed to be 4, or was it probably more generally?
Actually, it's generally, right.
Women?
The problem he gave, the assignment was only 4. Okay, the sailor problem originally given by Ben Ames Williams was about 5.
The problem was to find itself.
Right, 5 sailors at that time. That was back to 1926, October 9. This is a very old paper. It's a Saturday Evening Post, appeared as a short story by Ben Ames Williams. And this problem was solved by the Nobel laureate physicist professor. This is why we had difficult time to track down the source. And also by Professor Whitehead. So these 2 gentlemen, one is Nobel laureate Professor Dirac, he solved this problem, and also Professor Whitehead. So this is quite a long time. But the point is, even though you can write a computer program for the 6 sailor, for 5 sailor, and for 4 women, then the key issue is that suppose I have 10,000 people in the game, then how many cocoa nuts should be in the pie, and many other issues involved. Now, is there any more question about the problem? No, then I proceed to finish it, which is very fast, okay? We assume that there's N nuts in the pie and P women in the game, and W is the amount of nuts hidden by the first woman, with R's of 1 nuts left over. Okay? The next slide. Continue. W2 is the amount of nuts hidden by the second woman with R2 sub 2 nuts left over. So continue this way. We proceeded. W sub R is the amount of nuts hidden by the R woman with R sub R nuts left over. Then P, this P now, the R is really an index between 1 and P. P is the total number of women involved in the game. R means I pull out a certain index, a certain cardinal number. R is the cardinal number, number 4, number 5, number 6 women. So this is very clear, I hope. Now we can form a table. This table is that the nuts hidden by each woman, namely number R woman. We proceed one by one again. W1 is the number 1 woman. See, since she gave 1 nut, has 1 nut left over to the monkey, take the total nuts minus 1 and divided by the total number of women P in the game. That should be the first pile of nut, woman number 1 hidden. Okay, she get the first cut. Then what is left should be P minus 1, whatever she got. That's why P minus 1 times W1 is what are the nuts left. Okay? Now you reduce that with reduction or without reduction, it doesn't matter. Now continue this way. The second woman, take what is left over and minus 1, again divided by P, that is the second woman hidden the number of nuts. And then you take P minus 1 again times W2. That is what are the nuts left over after the first and the second one taking away the nuts. Now continue this way. Continue this fashion. You have W3 and R3 and number R woman and the nut left over. And finally, you can write a general form of the nuts that the woman, number R, hidden away. And that's the total in the bottom here. Again, the nuts left after the number R woman taken away, what is left over is this R sub R. Now when R equal to P equal to the last woman taking the nuts, means RP. Then you substitute whatever you get from R there, that is reduced into this form. Now equation 1 represents the nuts left over in the next morning. This is a very important equation. So the last woman hiding her own share of nut, the total nuts left over is represented by equation 1. Now the last woman is the P woman. Hit the amount of nuts, WP, is represented by equation 2. This is number 2. Okay? Again, in the next morning, the leftover nuts, amount of nuts, RP, in equation 1, is to be divided by the P woman and gave 1 to the monkey. Then, you can write the third equation. So you take all the nut left over 9 after the last woman taking her share of it. -1 divided by P, because they had to divide this nut left over in the next morning. That should be equal to a certain integer. That's equation number 3. Now, I don't even know what's the integer because I don't know the number. Fine. Now with all this equation 1, 2, 3, let's calculate some more terms. Now the net gain of nuts by the number of women is denoted by TR. This TR should be equal to WR plus what she last get, the I. And you sum this up and you end up with equation 4. Now after you get representation from equation 1, 2, 3, 4, then you substitute RP from 1 into 3, equation 3, and then simplify it. You end up with equation 5. That is the key equation that you can get a complete closed form solution of it without reducing a lot, spending a lot of trouble in finding the Diophantine equation. Now look at equation number 5. The problem is now reduced to find n and I as integer that will satisfy equation number 5. For any given woman, number of women P, as a total number of women in the game. Now you look at, even by inspection from this equation, obvious you set n plus P minus 1 equal to P to the P plus 1 power. Am I writing it right? Yes. And the next line, 1 plus I equal to P minus 1 to the P power. Then these two signs must be identical. From here, you simply deduce to the solution into equation 6 and 7. N is equal to whatever is P to the bracket P plus 1 power minus P plus 1, and I is the last pile of nut each woman get, P minus 1 to the P power minus 1. So that's the general solution of it. So this is a complete solution. Then we can check with the number. There are many, I don't want to spending too much time then we get all the TR, WR, and so far so on. Finally, I think I will give you the number of example as an example. Now the N is the number of nut. P is the number of women in the game. At least 2 women to play, then the nut should be 7 of them. And the WR is the nut that a certain number of women will get. Number 1 get what, number 2 get what. The result are here. There are 2 more columns there. I don't think it's worth to repeat again. If P equal to 3, you get the number of nuts is 79, and P equal to 4 is 1,1021. Number 5 was the Ben Ames Williams original sailor problem. And I think Adam Warren was asked for solution number 4. But obvious from the formula we got, you can solve unlimited number of problems. Unlimited number of P as an input, then you get all the solution. Now what is the conclusion on this simple solution? Number 1, the current complete solution is in closed form. without solving the simultaneous linear equations of congruence. Suppose you have 1,000 women. You reduce the 1,000 simultaneous equation. It's pretty troublesome. Number two is advantage over all the other previous solutions by means of the reduced Diophantine equation are 2 points. A, it will save a great deal of computing time to obtain the solutions, especially when the number of women P in the game is a very large number. Number two, provide the complete information of the solution of the problem that has never been obtained before, such as WR, WP, TR, and TP. So that's it. This is a very simple analysis, a very simple conclusion. Yes?
Just maybe I missed this, but I guess you were trying to get a minimum solution when you saw the Diophantine equation or whatever.
Which is because both sides is divisible by the LCM, which you divide both sides is only equal to 1. Otherwise, you can multiply both sides any number you want. Both sides equal to 1, that's the minimum integer, right? So I think that's the advantage using this. Now, I do not see Professor Herder's computer program that he wrote or he had or from any other students. So far, that's what we claim. We have an alternate that complete the solution, which does save a lot of computing time. And this brings up the question that I asked Professor Snell a moment ago on the stock market problem. We can do the same thing with the stock market problem, namely from the physics and mechanics point of view. Suppose you have 1,000 rubber bands. Each rubber band is has its own characteristics. It can be nonlinear. It doesn't matter as long as you can plot in graph. I don't care, sinusoidal, piecewise, continuous, it's okay. But you use the fundamental physics law. You can balance the input energy or even just based on the first law of thermodynamics under the adiabatic condition. And you can derive the Castigliano theorem in general, which is modified, much broader than the original Castigliano theorem. And you can get a closed form solution of the entire nonlinear system. Now, this problem was not known until 1978. It was closed door presented at UCLA. That's why I asked Professor the problem when UCLA got it. Okay, if they got it, maybe in '78. Now this has never been released to the public at all. Now we had a lot of solution which is not released to the public or not being accepted to the public. This is one of them. This paper was submitted and was written and sent to Dr. Gardner, but he never returned the work. I don't think it's fair to Adam at all, okay? And this is why I want to back him up as a MAA member and present this problem and let you have the judgment. In fact, this time I did submit 2 papers. The other is related to Professor Snell's targeting problem, so to speak, which right now I'm still in dispute with National Science Foundation as well as ONR, Office of Naval Research. That was the problem exactly that I asked your help, and see if we can confirm the number such that we can proceed many other problems, including experiment, including tracking of satellite. So we do have a number of closed form solutions. haven't been proved, haven't been supplied, haven't been documented, but not in the public domain. I think it would be nice that if I'm given an opportunity to talk to you about those problems. Unfortunately, Professor Sandifer don't want that problem to be appear here. Instead, choose the coconut problem, which is not so serious. So I would rather like to talk to you about a serious problem and try to get your confirmation. Because there has been a war with many physicists in the past 30 years. But finally, I think the U.S. Patent Office still approved it and given out the patent in 1992, and which actually was invented in 1974 as a result of my review of evaluation of the similar problem done by many companies at that time. It took me 18 years to fight for its survival. And in the meantime, because of that, we need confirmance from you gentlemen as a pure and applied mathematician from the rigorous point of view of mathematics. Now, I'm not using you to fight off the physicists, but we want to confirm some problem, just like this one. I think the solution is correct, okay? The advantage, just like what I said. Similarly, the other several problem is the same kind of category and same kind of characteristic, which needs to be confirmed, which will be beneficial to our graduate student and undergrad, since we are talking about reform of calculus and many subject area in high school mathematics. I think we do need owe to our youngsters something morally. Besides, some people may be concerned about getting rich and getting the big contract doing the ATR, automated target recognition problem by industry.